Hello. Today I'm going to present our work on estimating the shape of deformable linear objects with our proposed algorithm in real time. The project is motivated by our clinical application, robot-assisted transcranial magnetic stimulation, or TMS. TMS is a non-invasive brain stimulation that uses a changing magnetic field to induce an electric current at a specific area of the brain. The use of a robot can help to improve stability and accuracy in this procedure. By enabling force control of the robot, we could potentially ensure contact safety between the robot and the subject and compensate for the misalignment introduced by motion of the head. Although contact force between the head of the subject and the TMS coil is key to facilitating force control in this paradigm, it is impossible to directly measure due to the existence of a strong magnetic field around the TMS coil. Broadly speaking, force control of the medical robots is heavily impaired by the non-constant external force induced by the deformable load attached. Among them, deformable linear object, DLO, is a common type of deformable load in robotics applications. We believe that given the mass and material properties of the DLO, it is possible to perform both static and dynamic analysis by simulating the object's configuration as a cable in its operational shape. However, due to the specific clinical application, some special challenges are posed, which require a fast algorithm with accurate object detection, and the algorithm should be robust under occlusion. Some related work is shown here. In 2021, Wang et al. Reconstructed the shape of a rope from RGBD images. Similar work has been done in surgical applications, where endoscopic images are used to reconstruct the suture thread. The limitation of such image-based methods is the requirement that a high-quality segmentation mask must be obtained to gain good reconstruction. And we know that the quality of the segmentation often depends on the complexity of the background. The proposed method in this work aims to address this limitation by using an optical tracker and a novel algorithm. The method is called PCLG, which is Probabilistic Continuum Key Point Labeling Graph. The whole paradigm involves 3 steps. First, we use the optical tracker to track the retroreflective markers attached to the DLO. Second, the detected markers are considered as the key points, and we connect the KP based on a Euclidean distance threshold. At this point, we would have a graph with a lot of redundant edges, and each KP can have multiple edges. Last, we apply probabilistic edge pruning, PEP, to cut the redundant edges and reveal the real connection in the graph. PEP is the core component of PCLG algorithm, and we will introduce it in the next slides. The shape is estimated through piecewise interpolation of the processed graph. So the implementation of the PCLG algorithm is based on a very simple assumption, that is piecewise constant curvature. As you can see in the figure below, any 2 consecutive key points can be connected by an arc. The length of the arc is predefined by the interval of the corresponding retroreflective markers. The key points are the detection results of the retroreflective markers gained from the optical tracker. The graph is initialized by using these KP as the nodes. The edges are formed according to the Euclidean distance threshold. Usually, the threshold is set to be double the distance between the actual spacing of 2 neighboring markers. From the previous description, if we know the position of one key point, the potential positions of its consecutive neighbor are constrained, under the assumption of piecewise constant curvature. Additionally, by counting for the noise of the detection result and the accumulative errors, a probability field that indicates the possible position of the next point can be established. Through this field, we can evaluate how likely one point is the next point of the current one. The probability is calculated based on a 2D configuration. From the previous description, if we know the first point of this graph and start to search from this point, we can generate the probability field around this point and evaluate its connected neighbors to see which one has the highest probability. After the most probable next point is found, we can reject all the other edges coming out of this point. The most likely neighbor will be used as a stem to generate another probability field to find the third one. By iteratively applying this rule, we can cut all redundant edges and retain the actual connections. PCLG can be extended to 3D scenario. We can find a plane in which one of the neighbors resides and that is perpendicular to the cross-section of the DLO at the current key point. Within each normal plane, the problem falls back to a 2D planar setup. We can use the same steps in the previous slide to calculate the probability of each neighbor. After pruning the edges, In step 3, a piecewise cubic interpolation is used to reconstruct the real shape of the DLO. To validate our method, we first applied Unity, which is a mature game engine, to generate realistic DLO with 24 segments. Here the DLO is constructed based on a spring mass model. Each joint of the model is a torque spring and non-extensible. The key points are manually selected from the joint anchors. A cylinder is put next to the DLO to mimic the obstacles that could block the key points. You can see that when the DLO is partially occluded, we lose track of one marker, but PCLG can still correctly estimate the shape. Here are the results that we obtained from the real experiment. We used the RealSense to capture this video and project the results of PCLG to the RGB image from RealSense. The projection is denoted as a red dotted line shown on the left. You can see our method works pretty well either when the operator is trying to move the cable or when the markers are blocked. Our proposed method is capable of handling partial occlusion while producing a high-fidelity estimation. Moreover, PCLG improved the tracking accuracy by incorporating optical tracker results. Our paradigm also reaches real-time capability, and it is robust to the shape and type of the DLOs. Thanks for watching.